In this video, we'll talk about Laurent series, which are just like power series, except you allow negative powers, and these will be a way to represent analytic functions on annuli. And one of the really important applications we'll get out of this is Riemann's removable singularity theorem, which says that a function analytic on a punctured neighborhood of a point, and if it's bounded on that punctured neighborhood, then it extends analytically to the point that you've removed. The chief tool that we'll use is a version of the Cauchy integral formula for annuli. Before we get into Laurent series, it helps to talk about the notion of being analytic at infinity. And before we even do that, it's worth talking about a neighborhood of infinity. So U inside the complex plane is a neighborhood of infinity if there exists an R such that all points with modulus bigger than R belong to U. So it's sort of U is a neighborhood of infinity if it contains all points beyond some disk. And we're going to say that F, defined on a neighborhood of infinity, is analytic at infinity if F of 1 over Z extends to be analytic at 0. So F of 1 over Z, we can talk about that being defined on a neighborhood like Z such that 0 is less than modulus of Z is less than 1 over R, so it's a punctured disk, and we just want this to be analytic at 0. Now, what does it mean to be analytic at infinity? Well, if you're analytic at infinity, then F of 1 over Z is analytic at 0, so it will have a power series representation. And if we put 1 over Z back in for Z, then you can extract out a formula for F that's valid on this neighborhood of infinity. And what you get is, well, it's helpful to take out the 0 terms because I don't want to take Z to the minus 0 because that might be confusing, but in any case, you put in 1 over Z into this formula and you'll get a series involving negative powers of Z. And we declare that F of infinity in this situation is just A0. So it would just be the value of F of 1 over Z, which you extend analytically to 0, you just find its value at 0. So what's an example of being analytic at infinity? Well, let's take rational functions. Take Q and P polynomials in the variable Z, and if Q has degree less than or equal to the degree of P, let's consider the rational function Q over P. And so I can write this out as a polynomial with coefficients Q0 plus Q1Z all the way to QnZn, where I'll set n to be the degree of P. And it's possible that Qn here could be 0, but we'll allow for that. But we do want to make sure that since we're saying that the degree of P is n, Pn should be non-zero. Okay, so we just have this rational function, and I claim it's analytic at infinity. Well, we just have to look at it at when I plug in 1 over Z. So what happens when I plug in 1 over Z? Well, I get this on the top and something similar on the bottom. And now I can clear the denominators and multiply the top and bottom by Z to the n to get this formula here, which will now start out at Q0 Z to the n, and then the terms will go down in powers until I get Qn and Pn in the bottom. And so this is perfectly analytic at 0 because Pn is non-zero. So I can plug z equals 0 in here with no problem. Okay, so rational functions where the top has degree less than or equal to the bottom degree will give you functions that are analytic at infinity. Okay, so our goal here is to decompose analytic functions on annuli. So here's what I mean by an annulus. So it's just all z's in between with modulus in between two values. So I have little r and big R. We do allow little r to be 0, and we do allow big R to be infinity. There's no reason not to. The case little r 0 is especially important because this will be how we study analytic functions with a singularity at one isolated point. Okay, and so our goal is to show that if f is analytic on an annulus, then it can be decomposed into a function analytic on the disk of radius r and a function that is analytic at infinity and for z's with modulus bigger than little r. And now this part, f0 will have a typical power series representation, whereas f infinity is going to have what's called a Laurent series representation, or it'll be a power series with respect to negative powers of z. And this whole thing is also called a Laurent series. And so this is what our goal is, to find Laurent series representations for analytic functions on annuli. So a Laurent series, again, is just one of these sums in powers of z where you allow negative exponents. And these will end up converging absolutely, so it won't matter how you do the doubly infinite sum. Let's just see an example of some Laurent series. Here's the function 1 over 1 minus z plus 1 over 2 minus z. And so this function is analytic everywhere except at 1 and 2. And it turns out we can get one Laurent series representation on the disk of radius 1, and we can get a different Laurent series representation on this annulus here, where the modulus is between 1 and 2, and then we get yet another one for all values, for all points where the modulus is bigger than 2. So let's just go through these. Well, on the disk, on the unit disk, we just get the power series representation because this is analytic at 0. I won't go through that because that's sort of familiar stuff. I guess the main thing is when dealing with, well, the first part we use a geometric series, and then the second part you factor out the 2, and then use a geometric series to write this piece. Okay, but what do we do on this annulus? Well, we can still use the power series representation for the second piece, but the geometric series that we used here in the first case is only valid for z less than 1 in modulus, so we have to do something different here. And so what we do is we take 1 over 1 minus z, and we pull out a negative 1 over z, and we write it as 1 over 1 minus 1 over z. And now the point is this is less than 1 in modulus when z is bigger than 1 in modulus. So you can use a geometric series, but now it involves 1 over z. And so we get this here. So the resulting formula is a Laurent series for f on this annulus. And then you can do the same game on the set where z is bigger than 2 in modulus, and you'll get a formula for f that's all negative powers of z, and that just reflects the fact that this is a neighborhood of infinity and f is analytic at infinity. Okay, on the next page, we're going to look at the Cauchy integral formula on annuli, and that's going to be our main tool for proving that analytic functions on annuli have Laurent series representations.